Good morning to everyone. I'm Dr. Sumi MS. The topic of my today's presentation is synchronous design from Unit 3 Sequential Logic Circuits and Clocking Strategies. On completion, the students will be able to differentiate between synchronous and asynchronous sequential circuits and also be able to understand the occurrence of clock skew in sequential circuits. Sequential circuits are the fundamental components in digital systems and they are categorized into two types, synchronous and asynchronous sequential circuits. Both types have distinct characteristics based on how they are able to manage timing and also respond to the inputs. Synchronous sequential circuits are easier to design, more predictable and also better suited for applications where precise timing is crucial. Asynchronous sequential circuits offer faster operation and are better suited for dynamic environments but require more careful design due to their susceptibility to timing related issues. Synchronous sequential circuits. The synchronous sequential circuit is a type of circuit where all state variables that represent the internal state of the circuit change synchronously with a given input clock signal for the next state to be achieved. Such synchronization with a universal clock signal helps to ensure that all internal state changes happen at once, thus making it more reliable and less likely to experience race problems. Asynchronous sequential circuits. Asynchronous circuits are suitable for applications where speed is critical but at the same time timing control is less important. They are also useful in systems where power consumption needs to be minimized, and here as they don't require clock signal, power consumption is reduced. A race condition still occurs in asynchronous circuits when two or more state variables change in response to the input changes, potentially leading to some unpredictable behavior due to the lack of synchronization between them. Asynchronous circuits can be faster because they do not wait for a clock signal to change its state. But at the same time, the speed comes at the cost of some potential timing issues as well as design complexity. Clock skew. Clock skew refers to the variation in arrival times of the clock signals at different components or registers present within a single circuit. The clock skew can be either positive or negative depending upon the routing direction and position of the clock source. Positive skew occurs when the receiving register receives the clock tick later than the transmitting register. Negative skew is opposite to that. The transmitting register gets the clock tick later than the receiving register. Similarly, we also have zero clock skew, which refers to the arrival of the clock tick simultaneously at both the transmitting and receiving registers. The clock skew between two considered points I and j on an IC is given as del of ij is equal to Ti minus Tj, where Ti and Tj are the position of the rising edges of the clock with respect to that reference points. In the timing diagram given below, the rising clock edge is delayed by a positive value del at the second register, where this del is taken to be greater than 0. Clock jitter. Clock jitter is the temporal variation of the clock period at any given point. The clock period can reduce or expand on a cycle by cycle basis. It is also called to be as a temporal uncertainty measure. The cycle to cycle jitter refers to the time varying deviation of a single clock period. For a spatial location I, the jitter is calculated as I of n is equal to Tin plus 1 minus Tin minus T clock, where Tin is the clock period for the period n, Tin plus 1 is the clock period for the period n plus 1, and T clock is the nominal clock period. Jitter directly impacts the performance of a sequential system. Quiz questions on synchronous design. Differentiate between the synchronous and asynchronous sequential circuits. What are the different types of clock skew in sequential circuits? Thank you.